Hello everyone, I'm Sowmya Hassan Krishna. I'm a PhD student at Australian National University, and today I'll be discussing about the modulation technique, laser modulation technique, which we are planning to implement in the sodium monitoring for the laser guide star. Um, let's begin. So one of the problem with the wavefront sensor is the focus error. This might be because of atmospheric turbulence or from the centroidal variation in the uh, laser guide star when we observe. So it is necessary for us to differentiate because only correction should be applied for the atmospheric turbulence, not for the centroidal variation in the sodium layer. So we need a system which continuously monitors that sodium layer. Currently, there are two types of monitoring technique. The first one is the LiDAR technique, where a short burst of laser pulse is sent and the return flux is obtained to get the centroidal variation. And the other technique is the direct imaging technique, where we use a one mode telescope called X-ray telescope to observe the plume of the laser guide star at a certain distance. And when we observe it with certain offset, it looks something like this, which gives the profile of the sodium layer. But what is the limitation of this technique? In both cases, we need additional equipment. In LiDAR, we need a LiDAR. In the direct imaging, we need X-ray telescope, and we need to conduct both the operations simultaneously when we are doing the AO operation. So we need a technique, which reduces this limitation. So is there any technique which has overcome this limitation? And the answer is yes. There's something known as a laser modulation technique, where a laser is modulated with some pattern, and it is being sent to a target, and the written signal from a target will be cross correlated with the modulation pattern to get the uh, you know uh, required information. And this technique is widely used in ranging and satellite communication applications, and it's been used in from very long time. And the way the pattern the laser has been modulated will be based on a pseudo random bit. Let's see what is this pseudo random bit is all about. It is basically a deterministic periodic signal where bits are random, but signal repeats itself after some time. It's basically zeros and ones, and whose length is determined by 2 power n minus 1, where n it's a factor based on the round trip distance, the target, and the frequency which we want to generate the bit. And these are built by a shift registers. Say, for example, I have a length of 4, and I have to build a sequence. I can generate a sequence of like 15 bit, and perform, and this operation of generating a pseudo random bit is through the XOR operation. And the two input from the XOR operation are from the polynomial coefficient. And for each value of n, there will be a polynomial coefficient which decides which the output from which shift register should be taken for the operation. In case of 4, one of the polynomial coefficient is x power 4 and x power 3 and x power 1. So I'll be taking there'll be output from x power 3 and x power 4. The XOR operation is performed, and it is fed to the last bit, and the output will be the first output will be the first bit, and this process repeats for like 15 times for the 15-bit operation, and it goes higher if you're going for a higher value of n. And let's see how can we implement this in the laser guide star field. In our case, the source is the laser and the target is the sodium layer. And since we are interested in the modulation pattern of a laser, we have to modulate the laser to, because that's how we excite the sodium layer. And one more thing is we need a modulation pattern which should have a good autocorrelation property. So one of the type of the KRBS sequence is with that good autocorrelation property is the M sequence. So it's something like, first we modulate the laser according to that pattern, and then we send it to the sodium layer, which is the convolution operation of the sodium profiles with the modulation pattern with the noise will give the return flux on the detector. And when we cross correlate that detector with the modulation pattern, we're going to get back the profiles. And this is a demo of how things work. Here I've taken up a very simple, laser power, which is modulated between 0.1 to 1 in PRBS pattern. And this is the sodium profiles, which is spread across 75 to 120 kilometer with the column density of 2 into 10 per 15 atoms per meter square. And when we convert this, we are going to get the photons at the detector, which will be between 16 and 8 per milliseconds. And when we cross correlate that with the pattern, we get back the profile. And the question is, now, has this technique been implemented in the laser guide star field? And the answer is yes. It has been tested twice. Very first, it was in 1999 in Colorado Telescope. They were the first one to test this technique for the laser guide star. And they were successful, and they were able to get back the profile with 150-meter resolution. And then second time, it also they tested the technique, and they got back the profile. But the limitation what they had was the experimental results what they obtained for the centroidal variation did not match with the simulated results. So it is very necessary for us to check how the variation of an centroid depending on the different laser modulation depths. So that has still not been verified. So we have decided to, validate this technique again in Mount Stromlo, Canberra, Australia. So we're planning to implement this technique at the 1.8 meter EOS telescope at Stromlo, Canberra. And this is the laser guide star facility we have. And we are using a 20 watt EOS some frequency laser and costopic modulator for for modulating the amplitude, because this has a good output power. So we are using this, and also to run the AOM we need the RF driver, which generates the electrical pulse based on the modulation pattern which it is fed. So we'll be feeding the RF driver with the PRBS pattern. The modulated pulse from the AOM will propagate the optical path and will be sent to the sky through the laser launch telescope. And once it goes up there, the written photon from the sky will be collected on the primary mirror of 1.8 meter telescope, and it travels through the mirrors in the coil plug, and a part of it will be sent to a photon multiplier tube. In our case, that's the photon detector what we're using, and we'll be using the ADC to get the output in terms of digits. And again, we'll be doing a cross correlation at FGPA between the photon flux, and the PRBS to get back the profile. And to validate this technique, we are using one more technique, that's a direct imaging, to say yes, whatever we are getting in this technique can be validated, because we are using one more technique to get the profile. That's the direct imaging technique again. Here, we'll be using a telescope which is MSAT, which is located at 440 meter from the main telescope, which is 1.8 meter. And we can get almost a spatial resolution of 60 meter with this current setup. And so before we go ahead and start our experiment, it was necessary for us to see what are the parameters we have and what kind of values we expect from this work. So I carried out the simulation, and in which I've taken all the parameters at Stromlo, and I'm able to get the profiles, and I've added the noises. And yes, and the next step in this is to check how the centroid of these profiles are varying for different modulation depths of the laser and check if those values can match with the theoretically predicted values. And here are my theoretically predicted values. And these calculations are based on the equation which was previously done by Dr. Helmero. So it means in my case, I'll be getting 6.5 megaphotons per meter square per second for a 20 watt laser and column density of 2 into 10 power 13 atoms per meter square. And for 1 second, I'm getting around 1,200 meter centroidal error. And as I increase the laser modulation depth, this is going to decrease the error, and which in turn means there will be a reduction of wavefront error. See, for example, my values which are in red here at the 5 seconds, at some point, all the values will come below 100 meter, and which in turn is the value will be within 10 nanometer in the wavefront sensor. So it's good because for small telescope, wavefront error will not be a big issue. But as we go for a larger diameter telescope, yes, that will be in a higher. But it is necessary to see if our experimental values are gonna match with the theoretically and simulated values. That would be the future work with this thing. And also, we are planning to run a sodium monitoring campaign with this technique from the Q2 of 2021, because Sowmya is located at the 34 latitude, which will be under mid latitude range where the column density will be varying between a 3 between summer and winter, which will be a decent observation site. Yeah. So that will be our future plan with this project. And so in summary, I would say this is a widely technique in other fields. But in the previous tests, what has been done, there was a lot of instrumental errors, so the experimental data didn't match well, but they were able to demonstrate, yes, this can be used in the laser guide star field. And we are planning to, we can get the profile of 60 meter and even higher. And the main thing is the sodium monitoring campaign from this one site, and this is the site which never had any laser guide stars so far, and this will be the first time Australia will see its first laser guide star. Yes, that's all. Thank you.
Thank you very much, Sowmya. Are there any questions? I don't see no one in the Slack. Oh, there is one by Carlos Correa. So I suggest that you ask directly, Carlos, the question. I will mute myself.
Hi, Sowmya. Nice to meet you virtually. Nice talk about retrieving the CN² profile, and I was wondering, we don't have that much data, right? So I think it's useful to increase the database. But do you expect the profiles you'll be collecting to be different from the ones we have, especially in the north? And you gave a couple of examples. And also, if they are going to be different, can you then extrapolate from Mount Stromlo to other sites around the globe?
See, when it comes to a site, yes, Australia has never been done a sodium monitoring campaign. It itself is a new thing. And when it comes to data, yeah, probably we can, once we get the data from this site, we can try to compare it with the other site and check how different is it. Yes, probably that's one thing we can do in our future work.
Thank you. I'm going through the Slack, and there are no more questions. I do have a question, and I was just wondering if so the way this is done is that you send a pattern up, and because your time resolution is very high, you can actually see how what is the feedback flux. I'm just wondering what effects could could you have that will make your results don't go very well? So the first one is the pattern really zeros and ones, as you are saying, or the flux, let's say the acoustic, you have an acoustic modulator. How does it work in practice? And do you have optical depth effects in the sodium layer and time delays that will have some effect? Maybe not, but just wondering.
Yeah. So the AOM which is used will be modulating the power of the laser according to the pattern what we feed. It basically works on like a Braxel. Like the refractive index of the system changes when electrical pulse is sent, and that is basically on the sound wave. So yes, that's how AOM works. And the as we go for a higher resolution, there is something known as say the sodium layer will have its own spatial resolution. Say for example, it's the layer will be a same for like 100 meter, and I'll be modulating my system at 50 meter. So it makes no sense for me to modulate at a 50 meter and get the resolution of a profile to be a 50 meter, wherein sodium layer is varying at 100 meter. So I have to make sure the values what I choose for the modulation should be almost same to the variation of the sodium layer, both in terms of spatial and the temporal.